See
Yeah, we can see that.
my screen here. I'm Jack Terraconi. I'm here to was the project lead for the UAVSAR team, and we're here to present the work we did. And yeah, we're really excited about some of the stuff we got done. On the overview UAVSAR, we sort of stayed. We were going to split into subgroups, but decided to stay as one big team and sort of work on sub projects together and keep communicating. We felt like the teams might be a little too siloed at once. So sort of a scattershot of different products, but everyone sort of found what they were interested in and went with that. So we're really excited about that. We had two really big UAVSAR campaigns in 2020 and 2021, 14 sites, different polarizations, just a massive data set. At the place we're at with UAVSAR now, it's not, we really wanted to build some programmatic tools to access and have the data be accessed easily and analysis ready, because we dealt with that binary file issue that the way they produce the data. The whole sort of purpose of this work is to get ready for the launch of NISAR, because UAVSAR has an L-band INSAR on it. NISAR will have that on a 12-day repeat, and we're trying to build the knowledge base and the code so that when NISAR launches, we'll be able to use it and be ready to use it for doing snow-related research. Our projects fell into a couple different categories. One was looking just generally, bringing out a lot of flight pairs in and computing statistics about the coherence and the unwrapped phase to just sort of get an understanding of all the data and what we had. We wanted to develop new ways of looking at the data using the pulsar data, not just the INSAR, looking at SWE change as well. And then also looking at SNOTEL statistics and querying the database to bring them in for the UAVSAR flight lines and computing SNOTEL statistics that looked at the same time periods of the different INSAR pairs. And then we also, the thing that I think I'm most excited about is just forming a group to continue this work and a Hackweek repo that we were gonna keep putting into when this is over. So Jules, you can take it from here.
Sure. Hi. So what I did was to look at the polarizations from the UVASAR data set. So on the far left, you'll see a false color RGB using three of the polarizations, the HH, VV, and HH bands. We do some band math and artificial creation of secondary band information to create what we see on the bottom right. On the top, we can actually see the amplitude HH band and the entropy, which gives us an idea of the uncertainty across the scene. And what we do on the bottom panel here is to use the artificially created bands to do a principal component analysis. And from that, we can see the strongest features that are immediately shown in the scene. So you can see where the road is and where some agricultural plots are. So that's what I did from the data that was there.
Cool. And then Paul had to head out. These were his slides, but I can talk about them briefly. Paul spent his time working to develop a Jupyter Notebook and script that interacted with the Alaska Satellite Facility API. So this allowed us to automatically query using a Python notebook, and he even implemented some graphing and bounding box using Python as well in there. So you can query images and understand and download data using sort of the download functionality I had written in my tutorial, and he brought it in so you can do it all right here, which is really exciting because it's just adding another layer to the ease of access to this data, and you can do it programmatically as well. And then we also use some of Zach's code to put things on the S3 bucket, because we were having issues with downloading throughout. I think a lot through the Hackweek, a lot of those download servers were breaking because 80 people were trying to access them at once. So we did like these big bulk downloads with Scott Henderson's help, put them on the AWS bucket that we had, and then we're just accessing data through there, which made things a lot easier for us. Yeah, this is just the search download function that Paul wrote. It's, we have interferometry GRD is a lot of the data we were looking at in UAVSAR, and it pulls in whatever data is in the bounding box you decide to draw. So it's a really simple interface that we hope other people can use as well, because it's on our GitHub repo. It converts them into cloud optimized tips. You can change that as well if you want normal ones, and you could change it from downloading to the S3 bucket to your local machine, which I'll be doing after once we get off the hub environment. And yeah, it's in the repo. Paul did an amazing job. I can't believe he did this fast. It was really, really cool work. And then Ross, if you're here.
Yeah, thanks, Jack. Can you hear me okay?
Yep.
Great. So yeah, as Jack mentioned, kind of in that first slide, we have so much data, so many images to work with here. And some of these during this hack week, we opened and viewed really for the first time. And there are many more flight lines in Grand Mesa, but this is an example of a flight line from the Montana CARC site that we had a chance to look at. And on the left here, you see the overall flight line, which moves from kind of a northeast to southwest track. Northeast is all agricultural fields, and we kind of get into the Little Belt Mountains down into the southwest. And in this larger image, so this is an unwrapped phase pair, 2 images taken 5 days apart. So on the coloring here, the white indicates very close or almost no difference between the phase, so not much change. And then the darker colors indicate more change. And on this large scale image here, we can kind of see this very low frequency undulating kind of between blue and red colors. And that might indicate that we have some atmospheric effects going on that are introducing some artifacts into this image. So we kind of put that on the back burner. That's going to be something to address later on. But if we zoom in more on the right, the different agricultural fields become very apparent. And kind of what we're looking at here, the different red and blue colors, we can really see the boundaries of these different experimental fields where maybe there's a difference in the stubble height, excuse me. We might go from bare soil to 40 or 60 or 80 centimeter vegetation there. And right where that green dot is, we try to include some photos here down below. This is a windbreak feature that basically through the wind formed this really big berm on the leeward side of it. And so you can really see these dark blue and dark red speckles. And it seems that that appears to be a pretty legit signal based on what we were seeing on the ground. So, more analysis is needed here, but we are hopeful that, hey, we're actually getting a pretty representative signal of the snow that we were seeing on the ground there. So pretty exciting to open this image for the first time and see something that seems reasonable. So.
Eric.
Sweet. So my name's Eric. This week I worked on pulling in some local incidence angles, rasters, and then some analysis that can be done with them. The local incidence angle is really important, especially when we want to do some more snow-related analysis, such as getting SWE, or the change in SWE between pairs, or the change in depth between SAR pairs. It's a lot more important than on a satellite where you can kind of just fudge some numbers for an angle, because we're so high up when we're using UAVSAR, we're closer to the ground, so there's a lot wider ranges of angles across the image, across the scene. So I worked on creating a notebook to download the binary incidence angle files from JPL, because there's a big problem that a lot of the other files that we needed could easily be pulled from an API. Unfortunately, that's not the case for incidence angles. So to be able to do this extra analysis, we need to be able to get these raster files. And we sent out an email to the ASF folks, and actually because of this, because we asked, they're going to try and fix that in the future. So that'll make it so that this analysis is easier in the future, and we don't have to go through a lot of this difficulty in downloading the incidence angles. So just quickly here, you can see at the top with this equation, you can get a change in SWE between the SAR pair. And then below that, we can see an image that may look a little bit familiar. So if you were at the UAVSAR tutorial, you remember seeing a LiDAR comparison versus an INSAR, but it was depth on the LiDAR, and then the INSAR was just phase. So here now, since we have incidence angle, we can convert that phase change to a depth change. And now we have like a one-to-one comparison for some future analysis there. So that's about everything that I worked on here, but the future looks bright because now we're going to be able to access these incidence angle files through the API. So a lot of this analysis will be able to be done a lot more programmatically in the future.
Cool. Alicia and Maeve.
Thanks, Jack. So the SnowTel stations that fell within the flight paths of the UAVSAR were extracted and used to identify the depth change over the image pair duration. This was done through creating shapefiles for each of the flights and leaning on David Sheen's tutorial of the SnowTel on SnowTel and just adapting it a bit from there to calculate the depth change for the specific dates and stations. So here on the left, we plotted the change in depth versus the average phase change for the co and cross polarization. And these are showing for all pairs polled. So the surveyed locations that lined up with the SnowTel data included Grand Mesa, Lowerman, and the Rocky Mountain. While on the right, again, showing co and cross polarization, but with the coherence from each flight paired compared to this change in snow depth for the duration of the flight. So the SnowTel data gives us the opportunity to compare the results of the phase change calculated from the UAVSAR, but also allows us to identify if there was any drastic snow melt that occurred over the time period between each of the paired image pairs. And so we are still working through creating an overview of the change in snow depth, SWE, and temperature for each station for the 2019 and 2020 season. And so next, pulling in other ground truthing data that occurred on a time series similar to the flight times with more spatial variability will be the goal. Thanks.
Yeah. Zach, this is you, right?
About 3 minutes left.
Got it. I think.
Yeah.
Okay, here you are.
So a lot of the week was spent on developing the code to process and download all these images. But by Wednesday or so, we had the ability to download. So we ended up programmatically downloading and then importing into our A3 bucket 63 image pairs covering 2015 to 2021. Here they are plotted with their average coherence, which is a measure of the phase noise. So a measure of how much information we'll probably be able to get out of that individual pixel. You can see we have a lot in 2017, 2020, and 2021, as well as most of them coming from Grand Mesa. Jack, you want to go to the next one?
Yeah.
For each one of these, we had an unwrapped image pair, which was the unwrapped phase change in the coherence. And we extracted just scene-wide mean, standard deviation, and interquartile ranges. So for coherence, our coherence centered on about 0.5 on a scale of 0 to 1. And we did notice a noticeable difference between the polarizations, with cross poles having a significantly lower coherence, suggesting there may have been a little bit more interaction with the snowpack, though there's other factors that could be playing in there. Additionally, we noticed some interesting trends with the coherence dropping in a noticeable way as the days between the flights. So this is a pair of flights. So as we have more days, that coherence is dropping noticeably in these 63 image pairs. For phase change, it was again centered around 0. So most of the pixels weren't showing too much change. And we didn't notice too much of a difference in polarizations across the 63 pairs.
Cool. Yeah, and thanks everyone. Just some final thoughts. I was so impressed with the progress that was made with the ability to access this data and lay down the groundwork. Of course, we would have loved more time to get to more science questions, but I think sort of at the space we're at in this analysis, that's in the future. Really got to focus on atmospheric corrections in the future, I think, is the big thing we're interested next with UAVSAR and different environments that INSAR could work with, because right now Grand Mesa is awesome, but that's sort of best case scenario. So we want to start looking at slope aspect, canopy cover, snow wetness to sort of try to constrain where this technique is going to work for NISAR. And hopefully we're paving the pathway to do NISAR research, do snow related NISAR research. So really excited, and thanks to HP and Scott too for providing guidance and helping us organize this hack week. So thank you very much, everyone.